Hi, this is 5.3b. I went ahead and wrote up a problem to save some time, but let's work it out together. We're going to integrate from 0 to infinity of e to the negative 0.2x dx. Because this is going to infinity, we have to change this to a limit as b approaches infinity of the integral from 0 to b of e to the negative 0.2x dx. Okay, so let's integrate this right here. Okay, so that becomes e to the negative 0.2x divided by negative 0.2. And we're going to go ahead and go from 0 to b. All right, now what does this equal? It equals a limit as b approaches infinity. We're going to put the b right there, and we're going to put the 0 right there. All right, now 1 over negative 0.2 happens to be negative 5. And then we're going to take this negative sign and bring it down. It becomes positive. This negative times negative becomes positive, and this 1 over 0.2 is 5. When we put a 0 in here, e to the 0 power is just 1. So let's continue now. If b is approaching infinity, that means this number here becomes larger and larger and larger, which means this number becomes smaller and smaller heading towards 0, right? So we're left with negative 5 times 0. And the limit as b approaches infinity of a constant is just the constant plus 5, which equals 5. So this converges, we say it's convergent. Okay, let's do the next one. We're going to integrate from 2 to infinity of 1 over x dx. Because of this infinity over here, we're going to change this to a limit as b approaches infinity of the integral from 2 to b, 1 over x dx. Okay, now it's time to integrate. We know 1 over x dx becomes ln of x. So we're going to say this equals the limit as b approaches infinity of ln of x, and that goes from 2 to b. All right, now we're going to evaluate, put in b, so that equals limit as b approaches infinity of ln b minus ln 2. Okay, as b approaches infinity, this ln b will get bigger and bigger and bigger and bigger, so it goes off to infinity. And the limit of a constant is just a constant. So this just equals infinity, and therefore it is divergent. Okay, now we're going to look at something called the perpetual present value of a continuous money flow. Now this is going to be really interesting and something that business majors will probably utilize in their life as they start making their money. Okay? At first it may look a little confusing, but I'll show you how we're going to apply part of it. Okay? So again, this is called perpetual present value of a continuous money flow. Okay, so we would integrate from 0 to infinity of RT e to the negative RT dt. Now, if RT is a constant, such that let's say RT equals D. Okay, then the integration of 0 to infinity, where we replace RT with D, of e to the negative RT dt equals D over R. Now this may not be so obvious, so I'm going to show you how this works. And then we're going to utilize D over R. So let's go ahead and integrate from 0 to infinity d e to the negative RT dt. Because we're going to infinity, we're going to have to take the limit as b approaches infinity and the integral from 0 to b of d e to the negative rt dt. Okay, well this d, since it's a constant, we can pull it out of the integral. So let's go ahead and do that. We'll keep the limit sign where it is. We're going to pull out the d, and then we're going to integrate from 0 to b of e to the negative rt dt. All right, so let's continue doing that, which is infinity times d. This becomes e to the negative rt over negative r, and we're going from 0 to b. Okay, so let's go ahead and evaluate that. Limit as b approaches infinity, d times, and this becomes, we'll put a b in there, e to the negative r times b over negative r, minus e to the negative r times 0 over negative r. Okay, so when we evaluate this, taking the limit, we're going to keep the constant. We know this is going to go to the bottom, and what's going to happen to this? This is all going to go to 0. And then we know e to the 0 is 1, so that leaves us with negative 1 over negative r. All right, and so now we're going to multiply d times a negative 1 over negative r, and that will give us negative d over negative r. And what does that equal? Negative d over negative r. Correct. It equals d over r. Okay, very good. So now let's apply d over r so you can see how it's used. And this is really cool. I know I keep saying that because it really is, and it's something I wish I would have known a long time ago. So this is great that you're learning it now. Okay, so here's an example. Let's say you want $5,000 a month to live on when you retire. Okay, you want $5,000 a month to live on when you retire. And let's say at 65 years of age, okay? How much will you need? How much will you need to deposit now? To deposit, we're going to say in a 4% compounded continuously account, of course. All right. You want $5,000 a month to live on when you retire at 65. How much will you need to deposit in a 4% compounded continuously account to earn $5,000 a month? Okay, well, this is where we're going to take d over r. We know d is in years, so if we have 5,000 a month, we have to multiply that by 12 to make it a year. R we said was 0.04. So that is 60,000 divided by 0.04. And that happens to equal 1,500,000. Okay. All right, so that's a lot of money to have, right? How are we going to get there? That's our next problem, okay? How are we going to get there? All right, just want to write up the problem here, and then we're going to, on the next one I erase this, we'll actually do the problem. Suppose you invest S, this is an S, dollars per year continuously from 25, so I'm going to say continuously from 25 years old to 65 years old, to have a future value of $1,500,000 at a continuous rate of 6%. Okay, so how much will you need to deposit to get that? How much per month will you need to deposit till you turn 65? Okay, so important stuff here. All right, so now I'm going to do the actual problem. Now that you know what the question is, how are we going to get it to $1,500,000? What do we need to go ahead and deposit monthly in an account that's 6% interest, which is kind of hard to find these days. So we have future value equals S over R. Does this look familiar? It should. E to the RT minus 1. Okay, so our future value is going to be $1,500,000. All right, the rate is going to be 0.06, and the time is 65 years minus 25 when you start, which is for 40 years. Okay, so future value, 1,500,000 equals S. Do we know what S is? No, we don't. Okay, that's what we're looking for. Okay, 0.06 times E to the 0.06, 40 years minus 1. Okay, so we have 1,500,000 equals S, and all of this divided by 0.06 is going to be 167.05294. I always like to go out 5 decimal places, okay? Okay, how do we solve for S? Correct, we divide by both sides, and we get S equals 8979.19 per year. Okay, so is that our answer? No, we want to know how much per month, right? So we're going to take that and we're going to divide that by 12. And that means that we would have to pay for 40 years $748.27 per month. Okay, so here's your homework for 5.3. 1 through 13 odd, 37, and here's a hint for 11 and 13. Hint, 11, 13. Let U equal, so do substitution. And then I'm going to be sending you our last written project. It'll pertain to this very thing.